All right, so we're just going to take a quick second and try out the warm-up question here. Yesterday we were talking about using log rules and ln in order to solve for exponential equations with e. So we're going to take a couple seconds, see if you can solve. Let's round to give me like an exact answer and then give me an answer that's rounded to about 3 decimal places. All right, so this is what you should get. If I were looking for this to be an exact value answer, we would be expressing this as ln 5 subtract 3. If you enter this into your calculator, you should have got rounded to 3 decimal places, negative 1.391. Is that what you got, Grayson? Perfect.
No bonus mark for you.
Slope was.
He's saying no bonus mark for him because he didn't get perfect. That's what he's saying.
So what is the full?
All right, so today we're going to talk about derivatives of exponential functions. So we did our recap yesterday. And so we're going to take a look at the derivative of any exponential function to any base. So b here is just representing basically like any base of an exponential function, so any number there. And we know that we can prove derivative rules using Newton's quotient. So I'm going to let f at x be b to the x, where b can be any base. And of course that means that f at x plus h, when we go to use the Newton quotient, is going to be b to the exponent x plus h. So our derivative is going to use the Newton quotient, which is this. And we're going to enter in our 2 equations here. So b to the exponent x plus h minus b to the x all over h. All right, so we're going to use a little bit of exponent rules to help us here. So we have an exponent rule that says that when we're multiplying 2 like bases, we add their exponents. I'm going to use that rule in reverse. So if I have addition of 2 exponents, I should actually be able to write that as a multiple of b to the x times b to the h, because I know when I combine those 2 things that I'm going to get the same base but the exponents added. And then we'll have subtract b to the x all over h. Okay, so this is helping us a little bit because now we can actually do a common factoring step. Each of these terms have a b to the x, so we can actually remove that. And we're left with b to the h minus 1 all over h. Okay, so you're going to notice with a lot of these kind of like derivative rules, we did the same thing with our trig function proof. When we go to evaluate the limit, anything that doesn't depend on h can actually be removed from the limit. So I'm actually going to take this b to the x term. We're going to move it out front because we know that the limit as h approaches 0 doesn't affect something that doesn't have any h's in it. And then we've got the limit as h approaches 0 of this remaining function in the brackets there. Okay, so there's still kind of a problem here. If I input 0 for h, I'm getting 0 over 0, which is still indeterminate form, so that's still a problem. So we're going to do something similar to what we did with sine and cosine, and we're just going to see what is going on with the graph of this function. Now remember here, b is actually representing like a multitude of different bases. So it's not just as easy as plugging in the function. We have to plug in the function for a variety of bases of b. So we're going to try it with 2, 3, 4, 5, and then see if we can kind of figure out what the limit is approaching as we approach 0. And then we're going to see if we can create a pattern here to see if we can figure out what the derivative is. So we're going to take a look. We're going to analyze the graph for a variety of bases of b. So we're going to use this table. And we're going to try to figure out what this piece of the derivative is. So I'm going to slide over to Desmos here. It's right here. Okay. And I've got the function graphed. And we're just going to use a little slider for b. So right now I have the slider set to where b is equal to 2. And we're going to see what our values are approaching as we approach 0. So at 0, of course, doesn't want to mark it off for me for some reason. Getting really, really close to about 0.693. So I'm looking at the y-coordinate there. I know it's a bit tough to see. Maybe we can zoom in a bit. So super, super close as we approach 0 here to about 0.693. So I'm going to record that in our table, 0.693. And then I'll switch our slider to 3, and then we'll see what that approaches as we go towards 0. So switch the slider to 3. You'll see the graph changes a little bit. This is a different base now. And let's see what we approach as we approach 0 here. Well, it is undefined, yes, but we're approaching 0, so we kind of want to see like what value is getting, it's getting closer and closer and closer toward. So I would say we could probably say like this is really close right here, about 1.099-ish. Okay, of course we are undefined because at x there's like an undefined point there, right? So we're just seeing what we're approaching. So it looks like when we're at like 0.001, we're at about 1.099 when the base is 3. Okay, let's switch our slider to 4. Function's going to change a little bit again. Let's slide up here, and we're going to see if we can see what we're approaching as we get closer and closer to 0. Looks like about 1.385, something like that, 1.385-ish. Okay, and then we'll switch our slider to 5. And we're going to see what we approach as we get closer to 0. So it looks like we're getting close to about 1.613. Let's see if we can get maybe a little closer here. Here we go, we're really close now. 1.611, we'll say. About that. Okay. There is no visible pattern here. What are these numbers? I want to know if you guys can figure out what these values are. So think about things that relate to exponential functions. Can we figure out how these bases of these exponential functions, so this would be for the function like 2 to the x, 3 to the x, 4 to the x, 5 to the x, can we figure out this piece of the derivative and how those are potentially related to the exponential? I'm going to give you a couple seconds. Try some things on your calculator. See if you can figure out where these numbers are coming from. So Anita, what did you figure out?
It's just ln of the base.
Okay, so this right here is actually equal to ln 2, and this is actually equal to ln 3, and ln 4, and ln 5. Now ours were just estimates, but if we actually calculated the limit, like if we were able to calculate the limit, we would see that the limit is exactly approaching these values. So if our derivative, we know our derivative is going to give us back b to the x, and it's going to give us some multiple k, where k is this limit part. So what is k in relation to the base b? Derek, question? Yeah.
Like 1, 2, 3, 4, 5, they're like
What? This?
yeah.
So we're just testing different bases of b. So like what is the derivative when we have the function 2 to the x? What is the limit when we have the function 3 to the x? And so on. Because for this derivative, the b is representing like all possible different bases. So we're just kind of trying to see if we can figure out what the limit is approaching for all those different functions. Okay, so what is k then? Ln of b, yep. So dy over dx for 2 to the x is going to be equal to ln 2 times 2 to the x. And then dy over dx for 3 to the x is going to be ln 3 times 3 to the x, and so on. Ln 4 times 4 to the x, and then same thing with 5. Okay, so we can say if our base is b, then the k value that we're multiplying by after we do the derivative will get the base and its exponent back, and then we have to multiply by the ln of b. So ln of b being whatever the base of the exponential is. Okay, so that's our little proof. The derivative of our function, any base b to the x is going to be, you'll get back the base to the exponent x, and you will multiply by the ln of the base. That's the derivative rule for exponential functions. And then, of course, if we have other things going on, like in the exponent, we'll have to use some chain rule type stuff, and we'll rely on some previous derivative rules as we go here. Okay, so the derivative of e to the x kind of follows from the proof above. E we know is just a number. So if I try to find dy over dx, we know the derivative of any base b to the x, we get back b to the x. And then we multiply by the ln of b. In this case, b is e. So the ln of e. And what do we know about the ln of e, Michael?
It's 1.
It's equal to 1. So e is kind of this cool function where the derivative of e is actually itself. So when we're approaching that kind of, if we change the slider on Desmos over here to e, when we approach 0, we're actually approaching the value e itself. So that's why e is kind of like this cool function, or e to the x, I should say, because its derivative actually just gives us back itself. Anita?
What does the derivative have to do with the limit, though?
So the derivative has to do with the limit because when we go to actually prove the derivative rule, we get this part is like part of the derivative, and then this part right here is the second part of the derivative. So this part right here is actually telling us this is where we figured out that this is going to approach the ln, I keep writing that, the ln of b. So that's where that ln of b part comes from. Okay, so if I do the derivative of e to the x, I get back e to the x. All right, so we're going to practice a couple of these derivative rules here. Remember, your derivative rules don't go out the window just because you're dealing with different types of functions. So if you see a constant, the derivative of a constant is 0. If you see a constant multiple, you're just going to use the constant multiple rule, and so on. Okay, so anyone want to try the first one for us? What's the derivative of 2 to the x minus 7? Michael?
So what I really do, just bring the x down, just be like x.
Nope, not power rule. We're using the rule that we just proved above. Anita?
Is it 2 to the power of x times ln 2?
Yes, so it'll be ln 2 times 2 to the x, and the derivative of negative 7 is just 0, so you won't have that anymore. Okay, so exponentials do not work with like power rule, right? The x is now in the exponent. Power rule only works if your base is x, so you just need to be mindful of that. Okay, part B. Anyone want to try this one for us? Michael?
So I think for some reason I think we put like a ln into that and then get rid of the e. Okay, so then you go like the ln for e.
You guys agree?
I'm trying to learn this.
We get back the same thing. Yeah. So the derivative of e to the x is e to the x, and using the constant multiple rule, we just keep that 4 out there. If you really want, you can write 4 e to the x times ln of e, and then you can let that be 1, and then you can get back 4 times e to the x, but it's not really necessary. So we get back the same thing. Okay, how about C? Yes, this will be 3 ln 2 times 2 to the x. Okay, so constant multiple rule says just keep that constant multiple out front and do the derivative of the 2 to the x part. So we know the derivative of 2 to the x is ln 2 times 2 to the x. Okay, and then last one, who wants to try this one?
Of course.
Grayston? Yes.
My brain doesn't work when I see the test.
That was your four.
Ln 3 times 3 to the x. Derivative of the plus 1, derivative of a constant is 0. Okay. Good. So we're going to find the equation of the line that is tangent to this curve, y equals 2 times e to the x, when x equals ln 3. So anytime we find the equation of a tangent line, we've been doing this since Unit 1, we're going to find the derivative function first. What's our derivative of 2e to the x? Same thing. Good. And we're going to evaluate this derivative, let's say y prime at ln 3. And we learned this little rule yesterday. If I have e to the ln of something, it's just the something. So it's actually just going to be equal to 3. If you put it in your calculator, e to the ln of 3, you'll see that it gives you back out 3. So we actually get 6 here. Okay, so that's our slope of our tangent line. We also need a point on the tangent line. So yeah, it will end up being the same thing. When we evaluate y at ln 3, it'll be 2e to the ln 3, so we'll end up getting 6 for that as well. So our point will be ln 3, 6. And then we'll enter this into our y equals mx plus b function and enter in your point. And then we'll just plug this back in. If you really want, we could express this like, we usually don't common factor like a line, but if you wanted to common factor a 6 from that, you could. So either of these answers for me is acceptable. I'm good with whichever you decide. Yeah, we normally don't really do that with line because we want to keep the m intact so that we can see the slope of the line. But yeah, you could, if you common factor to 6 from all of it, I would be fine with that as well. Okay, so same process as always. Find the derivative, find the slope at the x value, find the point on the tangent line, plug it into y equals mx plus b, solve for b. Any questions on this one? We're good? Can I scroll here? Vanessa, you good on this? Okay. All right. So a biologist is studying the increase in the population of a particular insect in a provincial park. The population triples every week. Assume the population continues to increase at this rate. Initially, there are 100 insects. A, determine the number of insects present after 4 weeks. How fast is the number of insects increasing when they are initially discovered and at the end of 4 weeks? If you're looking for a rate, so how fast or how quickly is it increasing, how quickly is it decreasing, this is derivative, okay? We're looking for the rate of change of how the population of insects is changing at those particular times. So for part A, we have to kind of create an equation here. If you kind of remember back in grade 11 and grade 12, we had this A at t function equals A naught, and then you'll have like your increase value, and then it will be like time over the period, growth period, decay period, whatever you have. Okay, so in our case here, we're studying population, so perhaps we can call this P at t, population at time. And we're going to put in the initial population here. We're going to put in the growth or decay rate in for B. And then we're going to put in the, maybe I won't use capital P here, we'll put in capital T, which will be the tripling period. You should know how to create these formulas at this point. We've been doing this since grade 11. Okay, so initial population. What's our initial population of insects? 100. What's our growth rate? Tripling. And tripling period? So it's every week. So if we want to put this in weeks, we'll just say 1 week. So it'll be like t over 1. And this is asking us about weeks anyways, so I don't think there's any need for us to put this into days. So we'll just leave it as t over 1 week. Okay, so we can evaluate p at 4 then to find the population after 4 weeks. Okay, if this happened to say something like 10 days, I would probably put this week into days so that I have the same.
So T over 7.
Yeah, it would be t over 7 in that case. Essay, yeah? Nope, because we're just evaluating it for a given time here, so you shouldn't have to use log. So what do we get? 8,100 insects. Okay, so after 4 weeks, there's 8,100 insects. And then part B asks us to look a little further and see how the population of insects is changing at particular times. So at a time of 0, when they're initially discovered, and at a time of 4 weeks, or after 4 weeks. So we're going to find our derivative of our function right here, p prime at t. What's our derivative with respect to t here? So constant will stay, yes. And then what's the derivative of 3 to some exponent? Ln of the base, so ln of 3 times 3 to the t. Yeah. We will evaluate that once we go to evaluate, like at 4 weeks, but we also want to be able to evaluate when time is 0, so we're not going to plug that in yet. Okay, so for the first one, we're evaluating the rate of change in insects when they're initially discovered. That's at time 0. Okay, we'll just do like an approximation here. Okay, you should get, I'm going to round to the nearest 10th, so about 109.9. And then we need something per something. So what are we talking about here? Insects per week, yeah. Okay, and then the second part of this asks us to approximate how quickly the population of insects is changing after 4 weeks have passed. So we'll evaluate p at 4. Okay, and I guess this is also an approximation, so should get in your calculator 8,898.8 insects per week. Okay, any questions on this one? We're all good?